Advanced Algebra 2, Concept 10.5 Notes, Complex Numbers. So, we're still solving quadratic equations, and we're going to introduce the idea of complex numbers. Not all quadratic equations have real number solutions. When you graph these quadratic equations, the parabolas either float upward in the upper two quadrants or downward in the lower two quadrants. The parabolas will never cross the x-axis, will never have real solutions. But they do have complex or imaginary solutions. For example, the quadratic x squared equals -3. If you take the square root of both sides, you would have the square root of -3. That has no real number solutions because the square root of any real number is never a negative number. So to overcome this problem, mathematicians created an expanded system of numbers using what we call the imaginary unit I, and it is defined as I equals the square root of -1. I believe the mathematician Euler is credited with this. So the name imaginary unit is unfortunate because the number is not imaginary. It actually is an expanded dimension of numbers that has some practical use. And I know one of them is electric circuits. If we take I and square it, that means we take the square root of -1 times the square root of -1, which will give us -1. So note that I squared equals -1. Every time we end up with an I squared in our problem, we will replace it with -1 because we always want to work with real numbers if possible. The imaginary unit can be used to write the square root of any negative number, and we'll do that now. So let's go over some examples in example 1. Let's start with example 1a. We want to find the square root of -25. Think of that as the square root of -1 times the square root of +25. We know that the square root of -1 now is I, the imaginary unit. So we go ahead and write that. The square root of 25 is 5. So our answer to this is 5i. When we're given a problem to find a square root and the root is already in the problem, we do not put plus or minus as our answer because the problem is indicating which root they want. And you look to the front of in this case, the square roots. There's no sign, so that implies a positive sign. So we're giving the positive roots of these problems. Let's look at B. So the square root of -72. Think of that as the square root of -1 times +72. Now we want to break down 72 into factors, and we're looking for a factor that is a perfect square, and the biggest one that we can find. So 36 times 2. You might have been thinking of 8 times 9, but 36 is a larger square root than 9. So we want to break it down into our largest possible perfect square is what I meant there. So the square root of -1 is I, the square root of 36 is 6, and then we cannot evenly take the square root of 2. So that's how we write our answer, 6i times the square root of 2. C, we have -5 times the square root of -9. So think of that as -5 times the square root of -1 times 9. So the square root of -1 is I, and the square root of 9 is 3. So with that 3, we multiply it by the -5 that was already in the problem, which gives us -15. And then our I term just stands next to that integer. D, we have the square root of -4. So we think of that as the square root of -1 times +4. Square root of -1 is I. Square root of 4 is 2. Notice how I write the integer in front of the I, the imaginary unit. In that case, the I is functioning like a variable and the 2 like a coefficient. Problem E, the square root of -12. Think of that as the square root of -1 and then break down 12 into the square root of 4 times the square root of 3. Square root of -1 is I, the square root of 4 is 2, and we can't evenly take the square root of 3, so that just remains at the end. F, we have the negative of the square root of -36. So the square root of -36 will be 6i, because the square root of -1 is I and the square root of 36 is 6. And then we simply multiply it by the negative that is out front. And now lastly, 2 times the square root of -54. 54 we can think of as square root of 9 times the square root of 6. We can take the square root of 9, which is 3, and we multiply it by the 2. The square root of negative 1 is I, and then we can't evenly take the square root of 6, so that remains. Let's talk about complex numbers and just a little vocabulary. So complex numbers in standard form, it's a number that has a real and an imaginary part, a plus bi. So a stands for the real number part, and bi is the imaginary part, the I unit. So if you look in our real column, the form is we put it in a plus bi. So this is standard form where the real number part, a, is first, and then the imaginary part. A real number you can always express in complex terms with the imaginary part. So if you look at the examples, we have the real number 3. Expressed as a complex number with both its real and imaginary parts, it would be 3 plus 0i. Or negative 5 could be written as negative 5 plus 0i. That's written as a complex number with both its real and imaginary parts. Here's another example, 7 plus 0i. You write another one in yours. Now let's look at our imaginary column. So again, an imaginary complex number is in the form a plus bi, so the real number part plus the imaginary, but in this case, the real number part will not be 0 and the imaginary part will not be 0. You will see both. Like the examples 2 plus 7i, 8 minus I. Another example could be 29 plus 11i. So that is a complex number where both our real and imaginary parts have value. Pure imaginary, again, is in the same form, a plus bi, but our real number part has a value of 0. So the imaginary number 3i can be expressed as a complex number by saying 0 plus 3i, or 0 minus 12i. Or another example would be 0 plus 2i, or simply 2i. So now you've got a term, hopefully in your mind, of complex numbers. And so we can have a real complex number expressed as a complex number. We would show the 0 amount for the imaginary. We have an imaginary complex number where we would have value for both the real and the imaginary part. And then we have a pure imaginary complex number where we would simply have value for the imaginary part. Now let's do some operations with these complex numbers. To add or subtract two complex numbers, you add or subtract their real number parts and then their imaginary parts separately, and that's as far as you can take it. So if we're adding, notice we have the imaginary complex number 8 minus I, and we're adding the imaginary complex number 5 plus 4i. So I'm going to drop the parentheses, and then we'll add their real number parts, 8 plus 5, which is 13, and their imaginary parts, negative I plus 4i is 3. In B, we are subtracting two imaginary complex numbers. So we simply drop our parentheses, 7 minus 6i. We have to distribute the negative 1 to the second so that we subtract both parts. Then we combine the real number parts, 7 minus 3, which is 4, and our imaginary parts, which is 0. Finally, we have a real number minus an imaginary number plus a pure imaginary number, 13 minus 2 plus 7i plus 5i. So just using a little of our new vocabulary there. Now let's rewrite that without our parentheses. So let's distribute the negative 1 so that we subtract both parts of those. Bring down our 5i. Combine your real number parts, 11, and then your imaginary parts, minus 2i. So a complex number should always be written in standard form, which is the real number portion first and then the imaginary number. Let's do some more examples, and we're going to multiply now. So we'll distribute this 4i and come up with negative 24i plus 4i squared. So remember that I squared equals negative 1. So when we have an I squared in our problem, we replace it with negative 1 because we can, and then simplify. So our 4i squared term becomes negative 4. So written in standard form, that is negative 4 minus 24i. On B, we're multiplying, so I'm going to FOIL first terms, outer terms, inner terms together, and last terms. So now I'm going to combine what I can. So my 63 plus 8i gives me 71i, and I'm replacing the I squared with negative 1. Negative 1 times negative 14 is positive 14. Now I combine that with my negative 36, and I put my real number portion first, negative 22, plus my imaginary, 7i. For C, I'm going to drop my parentheses and just add those two imaginary numbers. So I add my real number parts together, 3, and then my imaginary parts to get the imaginary number in complex form, 3 plus 6i. All right, let's just keep practicing. So D, notice we have subtraction between those two imaginary numbers. So we'll distribute the negative to subtract the second term, and then combine like terms. Negative 5 plus 9i. E, we just have a lot of things we're subtracting. So we have a negative 4 minus that imaginary number, so we subtract both parts, minus that last imaginary number, subtracting both parts. Combine your real numbers together. Negative 4 minus 1 minus 5 is negative 10, and then your imaginary parts. So negative 1i minus 9 more is negative 10i. F, we're just multiplying these two pure imaginary numbers together, and we'll get negative 30i squared. Replace the I squared with negative 1, so our answer is positive 30. Let's distribute the I in problem G, 8i minus I squared, which is the same thing as 8i minus negative 1. Written in standard form, that's positive 1 plus 8i. All right, one more multiplication problem. So I'm going to FOIL that. First terms, outer, inner, and last terms together. I'm going to combine my like terms and replace my I squared with negative 1. That will become then positive 1, because it would be the negative of negative 1. As simplifying, we get 16 plus 2i. So hopefully now you're getting used to seeing these complex numbers in standard form, with the real number portion first and then the imaginary. We can use that now to solve quadratic equations. So we're going to solve x squared plus 4 equals 0. We're going to subtract our 4 over, and then take the square root of both sides. So the square root of negative 1 is I, and the square root of 4 is 2. Now, since we're showing and putting the square root into the problem, we need to show both the positive and the negative solutions. So our two imaginary solutions for this quadratic are positive, negative, 2i. So that would be a parabola that is somewhere in the upper two quadrants, not intersecting the x-axis at all. With B, the first thing we need to do is to add our 11 over, and we'll get negative 36, and then divide by 2. So x squared equals negative 18. Now we just take the square root of both sides. X will equal, and then just take each part of the negative 18. So the square root of negative 1 is I. Break 18 down into 9 times 2. The square root of 9 is 3, and then we can't evenly take the square root of 2. So our final answers are positive negative 3i times the square root of 2. On C, we simply just need to take the square root of both sides. So x equals plus or minus. We can take the square root of negative 1, which is I, but not the square root of negative 13, so it stays underneath. It's similar on D. We take the square roots of both sides. We cannot break 38 down into any factors that are perfect squares. Just 2 times 19, and those are both prime. So our final answers are plus or minus I times the square root of 38. You can see how important it is that you remember to put the plus or minus symbol in the problem to show that there is both a positive and a negative root answer. If we take the square root of both sides, we get x equals, breaking 8 down into square root of 4 times the square root of 2, equals plus and minus the square root of 4, which is 2i, times the square root of 2. All right, let's do 3 more to seal the deal. Hopefully you're really getting the hang of these now. So we need to add the 8, first of all, and we'll get negative 28. Taking the square root of both sides, we'll have x equals plus and minus. That breaks down into 4 times 7, so the square root of 4 is 2, the square root of negative 1 is I, and then we're left with the square root of 7, which stays underneath. Notice when we take the square root of numbers, we no longer need that operator, so the numbers are not written underneath the square root. Let's divide by 3. We've done this before, taken the square root of negative 8. So x equals plus or minus 2i times the square root of 2. Finally, let's subtract the 33 and then divide by 5. Taking the square root of both sides, we get plus or minus the square root, I times the square root of 6. I'm just going to highlight all of our imaginary answers to these quadratic equations. So notice when we have imaginary solutions to quadratic equations, they always come in pairs. All right, I know this video is getting long, but we only have 4 more problems to do. We're going to solve more quadratics. Another way to say that is find the zeros. So if you have an f of x or y, you simply replace it with 0. And then you solve your problem. So 4x squared plus 20 equals 0. Now let's isolate the x squared. So we'll subtract 20 and then divide by 4. So x squared equals negative 5. You know what's coming. We're going to have 2 imaginary solutions, plus or minus I times the square root of 5. With b, we'll do the same thing. So we will replace our f of x with 0, because we want to know what x is when our output is 0, our y value, our f of x. X squared equals negative 7. You know what's coming are 2 imaginary solutions. X equals plus and minus I times the square root of 7. Again, let's do another one with c. Replace f of x with 0. Negative x squared plus 4. So this time I'm going to add my x squared to the left side. When I take the square root of both sides, I get plus and minus 2i, because 4 has an even square root. Pardon me. And finally, with example D, we'll replace the f of x with 0, and then subtract our 1, divide by 9. Now watch this. We're going to take the square root of both sides. So the square root of negative 1, 9, think of that as the square root of negative 1 over the square root of 9. You know that the square root of negative 1 is I. We want to show plus or minus. And the square root of 9 is 3. So we can write that as positive and negative I over 3, or plus and minus 1/3 I. All right, that completes our 10.5 notes portion of complex numbers. And so in the next video, we will do the other half of concept 10.5, which is a method to solve quadratics called completing the square.